Combining conservation laws. A 15 kilogram block is attached to a very light horizontal spring of force constant 500 newtons per meter and is resting on a frictionless horizontal table, as you can see in the figure. Suddenly it is struck by a 3 kilogram stone traveling horizontally at 8 meters per second to the right, whereupon the stone rebounds at 2 meters per second horizontally to the left. So the stone hits the block, compresses the spring, and rebounds eventually at 2 meters per second. Find the maximum distance that the block will compress the spring after the collision. So if I concentrate on what is happening during the collision, the spring is relaxed, so there is no spring force, there is no friction. So when this stone hits this block, there is no external force acting on the system. So at that moment, because the spring is relaxed, net external force is 0. Therefore, the change in the total linear momentum of the system must be 0. So we find that linear momentum should be conserved. Okay, so we're going to write momentum conservation equation. So what is the initial linear momentum? Total linear momentum initial value is, it was a 3 kilogram stone moving at 8 meters per second in I-hat direction. So it makes 24 kilograms meter per second in I-hat direction. What is the final linear momentum? Finally, we have the stone moving in minus I-hat direction, so it's minus 3 times 2 I-hat plus after this rebound, the 15 kilogram block is moving with a final speed v final in plus I-hat direction. So the change in the total linear momentum must be 0. Therefore, the initial total linear momentum must be equal to the final total linear momentum after the collision. So we can see that the final linear momentum minus 6 I-hat plus 15 v final I-hat must be equal to 24 I-hat initial linear momentum. So the final speed we can find here to be 30 divided by 15, which is 2 meters per second. So this is the final speed of the stone. Now what is happening in the spring? So suddenly we have this block, 15 kilogram block, moving at 2 meters per second to the right. There is no friction on the system, so the total mechanical energy must be conserved. Delta K plus delta U must be equal to 0, since the surface is frictionless. Therefore, we must have conservation of mechanical energy, conservation of energy. And initial kinetic energy was 1/2 15 kilograms moving at 2 meters per second, so 2 square. Final kinetic energy when the 15 kilogram block compresses the spring fully will be 0. Initial potential energy stored in the spring is 0. The final potential energy stored in the spring will be 1/2 K maximum compression squared. So final kinetic energy 0 minus initial kinetic energy you can see this is going to be 30 joules. 15 times 4 divided by 2, that's 30, plus 1/2, the spring constant was 500 newtons per meter, delta x max squared minus the initial potential energy is 0, so we can calculate delta x max to be 60 divided by 500 square root. So this is 0.346 meters up to 3 significant figures. Okay, so in this problem we have first this spring is relaxed. It's attached to a 15 kilogram block. There's no friction on the surface. A stone, 3 kilogram stone, comes and hits this block with a velocity 8 meters per second in I-hat direction. During this collision process between the block and the stone, there is no external force because the spring was relaxed. So there is no spring force, there is no friction, therefore no external force, linear momentum must be conserved. So we write the momentum conservation, which gives us that right after the collision, when the stone rebounds with 2 meters per second to the left, 15 kilogram block will start moving with 2 meters per second in plus I-hat direction. Then we concentrate on what is happening to the spring. This block will have an initial speed of 2 meters per second, and the associated kinetic energy of the block will be converted into potential energy of the spring as the block will compress the spring, so that there will be a total potential energy stored 1/2 k delta x max squared. At that moment, the block basically loses completely its kinetic energy and therefore has an instantaneous speed of 0. With the 2 meters per second initial speed, if we write the conservation of energy, because the surface is frictionless, there is no external force doing a work on the system, delta k plus delta u equals to 0, gives us for delta x max 0.346 meters. That's the maximum compression of the spring when the initial kinetic energy of the block is fully converted into potential energy of the spring.